So hopefully you can see it.
Yes, we do.
Good. My work is, first of all, I represent National Aerospace University, HAI, and this work in this paper has been done together with Dr. Igor Turkin and my colleague Lina Volobuyeva. This paper will be discussing the good approach of moving hard real-time software and actually designing the hard real-time software that is supposed to work on the students' nanosatellites, namely CubeSats. Okay, so the structure of the paper will be pretty simple. We'll look into what is out there, what is used for today as the software for the CubeSats. We'll discuss the concept of using microservices and container architecture for mission-critical applications. And then we'll go to the experiments and discuss algorithms and hardware that was used for assessing the hypothesis in the paper. And then we'll go to the results and get to the conclusions at some point. Well, what is the CubeSat? Some of you might know, some of you might not. Basically, the idea was started pretty many years ago, actually in 1999. And the idea was to introduce the low Earth orbit and put it available for academia and commercial launches of the satellites. And the satellites are supposed to be of this particular size, this particular class, is supposed to be delivered as the parasitic load, meaning that you have a big missile getting to the orbit, and then you can just piggyback a few satellites, so they're delivered kind of for free. So that's the idea. And to have this unified, there were several definitions of what actually the size of the nanosatellite shall be, starting from 1U, which is 10 by 10 by 10 centimeters, and reaching actually to 12U. So the good, well-known example of really picking up CubeSats out there is Starlink by SpaceX. Okay, what is the situation with the CubeSats in Ukraine? Well, as we know, Kyiv Polytechnic University has been kind of streamlining in this field, and they have been pushing in 2014. They have been pushing their first set on the orbit, and actually that set is still out there, still working, still performing nicely. But unfortunately, among the 4 satellites, only 4 that Ukraine wanted to put up on the low Earth orbit, we actually have not that much success. And the most recent Ukrainian CubeSat that was actually sent there after the war has started was also polyethane HP30 that was supposed to be working now. But unfortunately, there was an error, and the satellite was not able to eject, or was ejecting but not working properly. So what happened in this situation is that actually we can see that so many satellites, only 4, that what Ukraine can do. Do you see my screen, by the way, because there is some question in the chat or what?
Yeah, we can see.
Okay, good. Sorry, I'm just browsing again. So unfortunately, among the 4 satellites, we have not many successes. And the most recent satellite actually went into a so-called DOA, dead on arrival problem. That's why we want to work with my scientific team to research, to find out the ways how to actually fight this problem out. And if you look into the statistical data, actually 26% of the satellites that are put on the orbit are dead on arrival. So that's really a problem. 43% are only partially doing its mission, and only 10.3% are performing the full mission scope. So this is huge problem, because we are sending so much money on the orbit and we are not getting out the business function. So that's really a need to improve the situation. So and what are the problems? Well, the problems of this infant mortality or death on arrival are cheap components, because those satellites shall be cheap. very short development period, because you have to really speed up to be able to have your seat free for the launch, because missiles are not waiting for the parasitic load. It's pretty high psychometric complexity of the software, because it's, well, satellites will do many different things. And also what is really a big problem is that the quality of the software is hectic. It's always pushed to the very end of the project, and verification validation gets too skinny and actually pushed. What we propose in our paper, and what is novelty here. First of all, we propose to use microservices approach for different functions of the satellite. Well, this is known in a big IT and also used in embedded systems. But then we want to combine the microservices approach with actually introducing the interpreter, the real-time interpretation engine that can interpret the business functions that are developed for the purpose of the CubeSat. And this is actually extremely new in embedded. And when we combine this interpretation machine to the FreeRTOS, that is, real-time operating system that is used in embedded and on many satellites, then this is completely new. This has never been used, at least according to my research, working with IEEE and Google Scholar and stuff. And then using this concept, we'll be developing the software. So why do we want to address the complexity? Well, you can see on the screen here on the left side, this is the typical breakdown of the functions and parts of the CubeSat, where you have onboard computer, you have communication system, you have electronic power source payload, and attitude determination control system. And on the right, you have the UML component diagram that is only for the onboard computer. So you can feel that, when you kind of put all this together, then you have a lot of components, you have a lot of different boxes you have to tackle to be able to develop good software and then test it. So how do we want to use microservices? Well, as you can see on the left side, formerly software was monolithic, so it was built into one piece, doing it all. Then we went to the microservices world, where we have data separated, then we have small business functions separated to different boxes that are doing actually absolutely the same what monolithic software was doing, but then they are developed separately. So you can test, you can actually simulate the different use cases for those separate functions separately, and that's make it easy. And then on the right side here, you can see actually how you can put this kind of microservices, connecting those by event bus, where you share the data in the WANs between different services, to different containers. And let's talk about what are the containers and how containers can be used for the CubeSat. So in comparison to the previous picture, where we had like each module doing their own their own firmware, the idea here is to break down the whole satellite function to the microservices and to the containers. Let's say we have communication module. Let's create a container that called communication module. Let's develop software in it using microservices approach. And that's the notion of this idea and of this kind of design approach. And to be able to validate this, because it sounds kind of easy to do, we want to understand if this approach will actually fit into real-time constraints. And the real-time is not really only the immediate speed you have to perform some calculation, but it's also repeatability. It's also readiness of the system to perform and function and stuff like that. So in order to move on, the first task that was solved was choosing the proper container engine, and that it was WebAssembly based. WebAssembly came from the web browsers, and it's pretty well known in the industry. And then one Ukrainian team within last 7 years have been actually developing really small engine that is called WASM3 that we used in our work as an embedded container engine. So if you look into the problems and advantages and disadvantages of using this container engine, that is in fact interpreter that can interpret different software that is developed, we actually have some tick marks we want to close by it. Software shall be simple and easy to understand. Yes, this is solved because we have software functions separated microservices and containers, so it's easy to read. Software shall be modular and extensible. Yes, by default, because that's what we get. It shall be portable. Big yes here because container can be executed on any theoretically any platform. Reliability, we have to look into it. And then we have real time with a big question mark, and that's what we're going to discuss now. So to be able to simulate and understand how actually the real hardware works, we took two platforms. On the left side, you have Raspberry Pi Pico. That is super popular, Steam platform. It's used everywhere. And we did two software implementations on native C and using the interpreter and FreeRTOS. And on the right side, you can see actually developed as part of my PhD work, fully tailored platform for the CubeSat. Because we want to use it for the upcoming National Aerospace University satellite. And that's what we obviously want to see how it performs. To be able to assess the performance, we took actually three typical and well-known in computer science algorithms. Two first ones are very widely used in embedded, cyclic redundancy checksum calculation, and then we have fast Fourier transformation, and we have the different cyclomatic complexities or O notion complexities like linear and linear rhythmic, and then we used just a bubble sort, just as a good indicator of performance that has quadratic time, quadratic complexity in big O notion. And to be able to do so, we actually used different data sets. And then we wanted, as part of this work, to compare the real performance to the complexity model that is defined on the right side of the screen here. So to be able to do that, we came up with the mass model you can see on the screen, where we wanted to test the performance on different data set vectors. And we introduced these models on the bottom of the page for bare metal implementation with the coefficients we want to find and WebAssembly. And what we get, actually, the findings were a little bit disappointing, to be frank, because we can see that actually, if you follow the graphs here, you can see actually that the native C code that was kind of pre-expected is super fast, of course, but the overhead of the containers was so big. Actually, we are talking about really a two orders difference in the performance, and that's what we found in this paper, and that was apparently too bad. If you look into the performance ratio comparison here on the left side, you can see what is the performance if we count the native performance as the 0 on the y-axis, then you can see kind of the relative ratio comparison of WASM3 based container engine, and this is apparently disappointing because this is really big overhead, unfortunately. So how do we conclude? Well, first of all, we found that using such a good containerization approach is too heavy for satellites. It's really good for development. It's really good for for developing at the same time in parallel by different teams, having less errors and stuff like that. But it's too heavy. So it's probably too much for the cheap satellites. So maybe for the big ones it's okay, but for the small ones it's not that good. However, we would like to state that it still allows to solve non-demanding from calculation performance functions, because it provides flexibility, it provides ease of implementation. And then one of the biggest problems that is typical as a scarce resource for the satellites is energy, because you have sun energy you have to preserve, and then apparently having too much performance used because of the overhead means that we can barely use this very nice container implementation process. However, our idea and our future work will be related to introducing the dual core solution, to splitting time critical and calculation heavier algorithms to be done in a smaller real-time processor, and then keeping the bigger processor using still containers and more simple business. I would say like communication, probably tasks and stuff, still being put into the interpreter-based implementation. That's all from me for today. I will be happy to answer your questions.
Thank you so much, Alexander. Any questions, please?
Nope.
Okay. I don't see the hand in arm. So I have a question. So, Alexander, if you
Yes.
if you design the software, so you for your specified goal, it's for mission. So and any special requirements to the software in such way, like memory, like etc.
Well, unfortunately, with the modern approach to software development, everyone can say, well, more memory is better. But of course, memory is, well, it became super cheap. Memory became super cheap. If 20 years ago memory was a big constraint, today it's not the big constraint. But because of radiation, in even in a low Earth orbit, we have to stick to ferromagnetic RAM. That is actually more expensive and also less in size. So that's how we want also to preserve the memory size. And then yes, we calculate. We use static code analysis tools to be able to actually assess the footprint of the memory and split the memory to two banks, basically. One that is used for the system functions, and second bank used for payload, for the mission of satellite. So we kind of split it to, so two teams who are working on the system software can use their own memory, and then we have a scientific payload or commercial payload in future that can be split in the memory footprint. Right now we have in the system, we have 16 megabytes of RAM. And for the small satellite like this, it's actually a lot of memory.
Okay, thank you. So we have no time for next for one more questions. So we are going to the next presentation.